I worked out some examples, checked my arithmetic because I did them very quickly. The procedure I'm sure is right. Just check that I didn't make any stupid arithmetic errors. If you also look in the answer key, there are some problems that are actually worked out in the answer key as well. I just wanted to make a couple of remarks about some of the material we did earlier. And also, I'm asking all of you to make sure, not only for this class, but all your classes, you do the student faculty course evaluations. You should have received an email from the appropriate office of the college asking you to complete the evaluations, and it gave you a link to your courses. So please do that. It's really very important. Okay, a quick recap, and then we want to move forward. Let me just get the appropriate material here. Okay. So let's go to the tablet. Okay. Okay, we're good. So I want to emphasize that probably one of the most useful way of working out problems is remembering that the CDF is very useful. So for example, if you're working with an exponential distribution, then it turns out a simple calculation gives you f of x as 1 minus e to the minus ax. So remember, this is the probability that x is less than or equal to little x. And in this case, it's really the probability from 0 to little x. So that's a pretty useful idea. Generally, when you're asked to work out probabilities, it's usually easier. For example, remember also that for the probability that A is between X is between A and B is nothing more than f of B minus f of A. So once you've computed f of X, capital F of X, the CDF, it can save you a lot of extra calculations just by using it rather than integrating every time. So if I, for example, gave you a problem and I want to know what the probability that, say, the exponential distribution lies between 1 and 2, and let's suppose little f of x is 2e to the minus 2x, then f of x for this particular problem is 1 minus e to the minus 2x. So the answer to this problem is just f of 2 minus f of 1, which is 1 minus e to the minus 4 minus 1 minus e to the minus 1, or just e to the minus 1 minus e to the minus 4, and that gives you some answer, and bingo, you're done. So usually it's easier to work with the CDF and actually doing computations, so you only integrate once to find the CDF. Okay, that's one remark. The other remark was I want to remind you of the change of variables formula. If f is either if y is equal to some function of x, and this is either an increasing function or a decreasing function, then we found the PDF of y is equal to f of x times the absolute value of the derivative of the x dy, where x is the inverse function that we can easily compute. Okay. One or two other remarks, and then I want to move forward. In section 3.1 as well, in some of the exercises, I defined the notion of a median. And a median is really something very simple. For a continuous distribution, it's very simple. It's better than in the discrete case, where I purposely ignored it. if you have any continuous distribution, say from A to B, where A could be minus infinity and B could be plus infinity, the median is that point where the total area under the curve is 50%. Say from A to M, if M is the median, the area is, you got 1/2 the area. That's the median. In the same way, I could define a percentile. I'll just use a letter P for it. The median is the 50 percentile. But suppose I want to find the x coordinate such that this is equal to P. When P is equal to 1/2, then we get what's called the median. X of P is actually N. If P is equal to 1/4, we get what's called the first quantile. These are terms they use in statistics. So I use these terms in the exercises. I don't really care too much about these. The median is usually a useful one. And it's that point which gives you 50% of the area. One can also talk about the mode. The mode is the most probable value. It's the value that maximizes the PDF. Those are just things they like to talk about in statistics, and I talk about them in the exercises for those of you who need more information about them. Okay. Today, I want to talk about the normal distribution. So I want to begin with an observation. If I let f of x be the following function, 2 pi e to the minus 1/2 x squared, from minus infinity to infinity, we all took calculus 1, and we all know how to sketch a graph like this. If you sketch a graph like this, it's symmetric about the y-axis. It has this bell-shaped curve. You will notice at -1 and 1 are its 2 inflection points. When its y-intercept is just 1 over the square root of 2 pi. This is a very important graph, by the way. I give you a better picture in the text. This, in fact, you'll see in a couple of minutes, it will be called the standardized normal distribution. Now, the following is I'm giving to you as a given fact. Given. We proved this in calculus 3. If you take the integral of this function from minus infinity to infinity, oh, I'm sorry, let me actually write the function. It will be 1. So in fact, this is a real PDF. It's non-negative. The total area under the curve is 1. And by the way, by symmetry, what does that tell me about this area? If the total area is 1, and if it's symmetric about the y-axis, what must this area be? Come on, nobody knows that?
Half.
Got to be 1/2, of course. And similarly, from minus infinity to 0 will be 1/2. Okay, now this PDF is so important, we give it its own name. I'm going to call, in fact, I'll choose a different variable for it as well. I just arbitrarily called it z, from minus infinity to infinity. This is the same function, okay? So now I want to begin with a definition. So we will take this as a given that this area is 1. I always prove this in my calculus 3 class. It's very easy to prove. I actually give a proof in the appendix. For those of you who took some calculus, if you want to see the proof is done using switching to polar coordinates, whatever that might mean. Okay. So here's definition 1 from the text. The random variable with PDF, and now I'm defining the PDF, f of x equal to 1 over sigma times the square root of 2 pi e to the minus 1/2 x minus mu over sigma quantity squared, where x goes from minus infinity to infinity, with sigma some positive number, is said to be the random variable x. Okay, I forgot to say. Is said to be normally distributed with parameters mu and sigma, and we indicate this by writing x is normal with parameters mu and sigma squared. So it depends on these two parameters, mu and sigma squared, or sigma. In the special case, when mu equals 0 and sigma equals 1, we have n of 0, 1, the so-called standardized normal distribution, and we write its PDF as phi of z equal to 1 over the square root of 2 pi e to the minus 1/2 z squared. And we call the random variable z. Z is n of 0, 1. So we like to call the random variable z when it's a standardized normal distribution. And by the way, I'm going to show you, because I just have these parameters, I'm going to show you that, in fact, the parameter mu will actually be the mean of this distribution. And secondly, the parameter sigma is actually the standard deviation. Right now, they're just two parameters, but we will prove that. Okay, so I've defined the standardized normal distribution. And by the way, remember, f of x is equal to the probability that x is less than or equal to x. So in the general case, this would be the integral from minus infinity to x of 1 over sigma to the square root of 2 pi e to the minus 1/2. I'll call it, instead of x, I'll call it t minus mu over sigma squared dt. In the special case, when we're talking about the standardized normal distribution, we call the CDF capital Phi of z, and that's just equal to the integral from minus infinity to x, 1 over the square root of 2 pi e to the minus 1/2 t squared dt. So This is just the CDF for the standardized normal distribution. By the way, I really have to show, I've given you the fact that this integral is 1. What I need to do is I need to show, and I'll just tell you how to do that. I really need to show that the following integral is is 1 also. That is 1 over sigma, the square root of 2 pi, e to the minus 1/2 x minus mu over sigma squared, dx is equal to 1. Here's the hint. Let z equal to x minus mu over sigma, then dz is equal to, oops, I forgot the dx here. Oh, I have it. Then dz is equal to dx over sigma, if we just differentiate this. So notice what happens. If I call this integral I, the limits are the same. If I put infinity in, they don't change. Notice this sigma and the dx give me a dz. And I get 1 over the square root of 2 pi. And then I just get minus 1/2 z squared. But this is what I gave you before. This was given. And that's equal to 1. Okay, so the first observation is that this is indeed, this general form I've given you is indeed a PDF. Next thing, okay. Linearity preserves normalcy. What does that mean? Well, that means the following. Suppose x is a normal with mean mu and variance sigma squared. Let y equal to ax plus b. Then y is normal, and I have to tell you what the 2 parameters are. I have to find these to be found. Okay? So I claim, in fact, there's an easy way of finding it later on, but right now, I claim this is easy to do. Okay, I need my glasses because I want to use the same notation as I use in the book, which means I have to be able to see what's in the book. Okay. So, hello, Mahamba. So we know f of x is equal to 1 over sigma square root of 2 pi e to the minus 1/2 x minus mu over sigma squared. Okay, we also know that g of y, since we just did homework on this, is equal to f of x dx dy. That's a change of variable theorem. And by the way, notice this is linear. And if we solve for x, we get x is equal to b minus y over a. So dx dy is minus 1 over a. So what do I get for g of y? I get f of x, which is b minus y over a, times 1 over the absolute value of a. And if we plug all this in, so I have 1 over sigma square root of 2 pi, e to the minus 1/2, x is equal to b minus y over a minus mu over sigma. I can make this look a little prettier, and there's a 1 over absolute value a. So this gives me 1 over the absolute value of a times sigma square root of 2 pi, e to the minus 1/2, and what do I get? I get, let me just rewrite it as I have it here. I write this as minus 1/2 y minus A mu plus B over A sigma squared. Suppose I let capital B be absolute value A sigma, and I let capital M be A mu plus B, then this becomes 1 over B square root of 2 pi e to the minus 1/2 y minus capital B, oh, I'm sorry, y minus M over B. So notice this is n of M B squared. So it's normal. So a linear translation preserves normalcy. Okay. Another result that we're going to use. So we've proven that it's okay. So if X is normal with parameters mu and sigma squared, and Y equal, say, AX plus B, Y is also normal with some new parameters, whatever I call them, okay? Y is normal. Next result. So suppose we look at the standardized normal distribution, which is n of 0, 1. Remember, that means the PDF is just simply 1 over the square root of 2 pi e to the minus 1/2 z squared, as z goes from minus infinity to infinity. I could define the moment generating function is just e of e to the t. In this case, the random variable is z, right? Well, that would turn out to be the following. 1 over the square root of 2 pi, the integral from minus infinity to infinity of e to the tz, e to the minus 1/2 z squared dz. Now, I'm not going to do the computations now. I don't want to spend time on some basic calculus. But notice I can write this as e to the minus 1/2 z squared minus 2tz, this part. And I can complete the square here, and then I can do the integration. If I do that, it turns out we get the integral that I gave you before, the given integral, which turns out to be 1. And this answer turns out to be something very simple. It turns out to be t squared divided by 2. E to the t squared over 2. So with a little bit of calculus, we could show the moment generating function is e to the t squared over 2. So that means the derivative of this, derivative of the t squared is e to the t squared over 2, and the derivative of that is just t. And if I evaluate that at 0, I get 0. That means mu is 0. If I take the second derivative, it will turn out to be, I don't want to spend time taking derivatives now. It will turn out to be e to the t squared over 2 times t squared plus 1. Simple product rule here. Remember, right on here. So m double prime of 0 turns out to be 1. Therefore, E of z is in fact equal to 0. V of z is 1. So for the standardized normal distribution, the mean is 0 and the variance is 1. In the general case, let me remind you, let's suppose we know that if given any random variable x, we could standardize the random variable by, in this case, by changing, subtracting mu and divide by sigma. So the question is, if I make this linear change of variables, so notice what that says. That says x is equal to sigma z plus mu. So what is m of x? Well, this is a linear change. And we learned in section 2.11 when we did moment generating functions, what this does, you replace t by sigma t, which means we get e to the mu t plus sigma squared t squared over 2 for the moment generating function for any arbitrary normal distribution. And now if you take the derivatives here, guess what happens? E of x will just turn out to be mu, and v of x turns out to be sigma squared. So this gives you the following fact. Again, I'm leaving out the messy details. I don't want to spend time doing the differentiation. Here I just use the translation property of the moment generating function. So effectively what we've shown is, given any normal distribution x with parameters mu and sigma squared, E of x is actually equal to mu and V of x is actually equal to sigma squared. So let me remark what this really tells you. If you look at a normal distribution, here's one, for example. Here's the mean. The inflection point, by the way, turned out to be the standard deviation. That comes from simple calculus. This is sigma, this width. That's where the inflection points are. Now, you could see if you change mu, what that does by changing mu, you move the graph to the right or to the left. And if you change sigma, for example, if you make sigma smaller, then what's happening is you increase the height of the curve, but it becomes not as wide. Remember, you have to preserve the total area under the curve to be 1. Okay, so sigma, what sigma does, it either pushes the bell part of the curve closer together if you make it smaller, or makes it farther apart if you make it larger. And then, of course, if you make it smaller, if you make sigma smaller, the top of the curve goes up higher. And all mu does is shift it. Okay, so we have, therefore, the normal distribution curve. And typically you want to find probabilities. For example, what's the probability if x is, suppose x is normal of mu and sigma squared? How would we find this probability? Well, this would equal to phi of b, remember phi is the CDF, minus phi of a. It's really, remember, the integral from a to b of 1 over all this stuff with the sigma, blah, 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 blah. But it's just equal to, well, it's not phi of b. I'm sorry. There's a mistake there. What it really is f of b minus f of a, where f of x is the probability that x is less than or equal to x. But this would mean, and by the way, remember, f of x in general is 1 over sigma to square root of 2 pi, the integral from minus infinity to x of e to the minus 1/2, say, of t minus mu over sigma squared dt. And this would mean for every different x, we'd have to be able to compute this integral, which we can't do, and in fact, we need tables for. So let me tell you how we get around that. It's really very simple. Okay, so let's suppose you wanted to compute the probability x is, say, normal with mu and sigma squared. And you want to compute the probability that x is between A and B. What you could do is the following. We standardize this problem. What I do to one side of an inequality, I'm sorry. Now, this is now the standardized random variable z. Let's call this number A and call this number B. This transforms the problem into this problem where z is standardized. So this is equal to just phi of B minus phi of A, where phi of x, or phi of z, I should say, is the CDF of the normal random variable, which means I only need one set of tables. So let me ask you to turn your attention to the table that's given on page 203. On page 203, I give you a table, and notice it's phi of z. It gives you the values of phi of z, which is the probability that z is less than or equal to z, which is the integral, which is the area under the curve, really, from minus infinity up to the z value of e to the minus 1/2 t squared dt. So let me illustrate. So let's suppose this is the value little z. What this is doing, the area under this curve is phi of z. So let's suppose you want to compute phi of 1.23. Well, if you look at the table, in the left-hand column, you go down to 1.2, and you move on over to the column, the 3 column, and you see the number, I can't see it, what is that? 0.8907, is that right? I get this value. And let me put my glasses on and make sure I read it right. 1.23 is 0.8927. Suppose I wanted to compute the value of minus 1.23. Notice I only give you half the table, basically. I only give you the table for positive values. So I want you to make the following observation. If this is z, this is minus z by symmetry, correct? So this area, which is what I want to find, is the same as this area, right? Now, to find this area, what I do is I can take the whole area and subtract off the area up until z. Right? If I take the whole area, oops, this should be right. If I subtract this from 1, what's left is exactly this area here. So in particular, if I want to compute minus z, in this case, suppose I want to compute phi of minus 1.23, it's just equal to 1 minus phi of 1.23. So I subtract, and that gives me the answer. Observe, by the way, that suppose I want to find the probability that A is less than or equal to Z, less than or equal to B. Well, this is just phi of B minus phi of A. Now, sometimes you're asked to do this problem. Oops, this is A. Well, according to what I said, this would be phi of A minus phi of minus A. But I just showed you that phi of minus A is 1 minus phi of A. So this gives me 2 times phi of A minus 1. Okay, so I can certainly compute probabilities using this table. It's a very easy table to use, and I'll walk through a couple of examples in a minute or two to illustrate the use of this table on a couple of actual probability problems. By the way, sometimes we have to do the problem in reverse. That is, sometimes I give you the interior number of the table, and I ask you what is the z value. I'll illustrate that in an example in a moment. Now, why do I really care about the normal distribution? That's maybe I should have started the whole discussion today with that question. And the answer is, it turns out that many different distributions can be approximated by normal distributions. And we're going to see that in the next section when we talk about the central limit theorem. So being able to work with the normal distribution is very important. So let's consider first a trivial problem. Okay, so I'll do example number 1 in the text. Let's suppose X is normally distributed. It has mean 4 and standard deviation 2. The problem is to compute the following probability, that X lies between 1.36 and 6.48. So what we need to do is we need to transform from this distribution to the standardized distribution. Now, so remember, Z is equal to X minus the mean divided by the standard deviation, which is 2. So if I want to compute the given problem into a standard problem, what I have to do is, for each of these values, I replace X by 1.36 minus 4 divided by 2. If I do that to X, this becomes Z, and this becomes 6.48 minus 4 divided by 2. And by the way, I always round off my answer to 2 decimal places because the table is given to 2 decimal places. So this gives me minus 1.32 less than or equal to Z less than or equal to 1.24. This is equal to phi of 1.24 minus phi of minus 1.32. I showed you how to handle negative numbers a moment ago. So this becomes minus 1 minus phi of 1.32. And now, if we look this up, what does this give me? If you go to the table and look up 1.24, what do you get? 89.25? One minus, and 1.32 turns out to be 90.66. And if I do the arithmetic, assuming I did the arithmetic correctly in the book, I get 0.7991. Not a very interesting problem, okay? First to admit that. But essentially it shows you that anytime you want to compute probabilities for any normal distribution, you must standardize it. And to standardize any distribution, remember that if I give you X, which has mean mu and variance sigma squared, if I want to find its standard, all you do is subtract mu and divide by sigma, and that would give you the standardized. In this case, we're working with a normal, which is Z. So here's a different question, okay? Given phi of Z is equal to 0.1093, find Z. Can anybody tell me right now, how do I know Z is negative before I even start the problem? Does anybody know why Z has to be negative? Okay, what's the area of this shaded region of the standardized normal distribution?
0.5.
0.5.
That's below 0.5.
So this number is less than 0.5, right?
Yeah.
Means the total area up to the Z value is less than 0.05. So that's telling me Z is somewhere around here. Okay, it's some negative number. Right? In fact, let me call it minus Z, if you want. And I know that this area is 0.1093. Well, that means that this area is 0.1093, correct? This little piece here. So if I subtract this from 1, I'm going to get this entire area, right? So 1 minus 0.1093 is how much? It's 8907. So now what I do is I look to the table and I look for the value 8907 on the interior. Make sure you're doing that right now. So I look for 8907 or the closest number to 8907. I think I rigged it. 8907 is 1.23, right? Hold on, I just dropped my book. Put this here and take care of it. So that means Z is 1.23. So this value must be minus 1.23. So here's an example where I have to work backwards. Anybody have a question about that? Okay. Normal distributions are really quite easy. So let me give you another variation of the same problem. And that's, I think, the last example I do in this section. So consider the following problem. Suppose exam grades are normally distributed with mean score of 83 and standard deviation of 5 points, with 5-point standard deviation. If the upper 10% of the class get A's, what's the cutoff? What's the lowest grade that gets an A? Does everybody understand the question? So I'm telling you, I am essentially the instructor wants to curve the exam. So here's what he's saying, okay? Here's my class. This is the mean, by the way. U is 83, but okay. And he's saying the upper 10% get A's. So this is 0.10. So we can find, by the way, in the Z range, this of course mu is equal to 0, right? Let me get rid of this. I'm looking at the standardized normal distribution. So if the upper 10% get A's, the upper 10%, no matter how I talk about it, are going to get A's. So what Z value corresponds to, so that means this part is 90%, right? So what's the closest value to 0.90 on the table? Closest value to 0.90, it looks to me like it's 1.28. Everyone see that in the table? 1.28 is 0.8997. So 1.28. So the Z value is 1.28. Now I know X minus the mean. What was the mean here? The mean was 83 divided by sigma, and sigma was how many points? 5 points. That gives me the Z value. So if I multiply through, so the X value would then be 5 times Z plus 83. I just found that Z was 1.28 plus 83. I whip out my calculator, and what do I find? I find the cutoff score is 89.4. So the lowest grade that would get an A in this course is 89.4. By the way, I can ask another question here, okay? Suppose the lowest 5% get Fs. So what's the cutoff there? So let's draw the picture again, okay? So this is a 5%, 0.05. That means the corresponding Z value would be 0.05, which means everything up to that Z is 95.95. So what's the closest Z value to 0.95 on the table? .95 is what? It's either 1.64 or 1.65. Let's say 1.65. you could have also taken 1.64, or you could have taken 1.645 if you want. It doesn't make a difference. So let's suppose I take this value. So the z that I want here is minus that. So my z value is minus 1.65. So again, I had x minus mu over sigma was z, or z was, or x was 5z plus 83. So 5 times minus 1.65 plus 83 would give you my answer. Okay. It's a fairly straightforward problem. I'm not interested in doing the arithmetic for you, but I believe we're done. So here's an interesting question. Suppose x1 is normal with mean mu1 and standard deviation sigma 1, and x2, oops, I just lost it, and x2 is normal with standard deviation mu2, I'm sorry, mean mu2 and standard deviation sigma 2. Suppose x1 and x2 are independent. Prove, students hate this word, prove 1, y, which equals x1 plus x2 is normal, and 2, find e of y and v of y. Okay. Well, I can actually do it in one step. Now, here's what students did. By the way, this exact problem was on an exam last year that I gave. I didn't use the word prove. I said it a little differently because people get frightened when they see the word prove. Almost everybody did the following. They said, well, look, e of y is equal to e of x1 plus x2, which equals e of x1 plus e of x2, which gives me mu1 plus mu2. V of y is equal to v of x1 plus x2. And by independence, remember I said they were independent? Did I say that? Yeah. By independence, that means this is equal to v of x1 plus v of x2, which is sigma 1 squared plus sigma 2 squared. And then they stopped. So all they did doing this, which is correct, by the way, is they proved that the mean is the sum of the means and the variance is the sum of the variance. But how does that prove it's normal? It doesn't. So you can do the whole thing the following way. Here's one way of doing this. M of x1 of t is e to the mu1 t plus sigma 1 squared t over 2. And by the way, you don't have to memorize this. It's right in the table. It will be given to you. M of x2 of t equals e of mu2t plus sigma 1 squared, sigma 2 squared of t over 2. And we know by the reproductive property of the moment generating function, the moment generating function of y, which is the sum of two independents, is just equal to the product of the two moment generating functions. Since they're exponentials, I can add the exponentials. So notice this is in the form e to the mt plus s squared over 2t. This is normal with mean M and variance S. And notice the mean is just mu1 plus mu2, the variance sigma S squared. And S squared is just sigma 1 squared plus sigma 2 squared. So this proves it because the homogeneity function uniquely determines the random variable. Let me get some light on in here. Okay, so this covers the normal distribution. Please make sure you do the homework exercises in section 3.3. And now I just want to start talking a little bit about the central limit theorem. I won't put that on this exam. The exam will cover through this material on the normal distribution, but I want to talk a little bit about the central limit theorem, at least as an introduction in the next 10 minutes or so. Does anybody have any questions on the normal distribution? This is really very easy to work with. This was the hardest problem. And by the way, what I just said can be generalized. If x of I is normal with mean mu sub I and variance sigma sub I, and let's suppose x1, x2, x sub n are all independent, then if y is the sum of all of these, then y is normal with mean summation of all the means, and variance is the summation of all the variance. So what I just did for the case when n equal 2 can be generalized to this case as well. Okay. The central limit theorem. I need to remind you of a couple of facts. Let's suppose x1, x2, I have a sequence of identically distributed independent random variables. That means every one of these has the exact same mean, and every one of these has the exact same variance. That's a given. Then you may recall, well, let me remind you, let me define two new random variables, S sub n, which is equal to the sum of these, the sum of the first n of these, and the sample mean, which is S sub n divided by n. And if you like, you could write it this way. I need to remind you about the following properties. Firstly, E of Sn would be the sum of all the expectations. So this gives me mu n times, and V of Sn by independence is the sum of all the variances. But each of those is sigma squared, so I get sigma squared multiplied by n. Now, notice x bar is S sub n divided by n. So I don't have to even work this out. I can use a property. Which equals to 1 over n times n mu. Well, here, let me remind you of the property. Which equals 1 over n e of S of n, which is 1 over n times n mu, which is mu. And V of x bar is V of 1 over n times S of n. Remember with the variance, when you take out a constant, it gets squared. Which is 1 over n squared times n sigma squared, or sigma squared over n. So let me just summarize. E of S of n is n times mu. V of S of n is equal to n sigma squared E of x bar is mu. V of x bar is equal to sigma squared divided by n. Okay. So I have these results. Now, I need you, you'll need to recall these results because this is going to really be our start next time. Suppose I wanted to standardize the random variable. So if I wanted S of n star, to standardize this, I take S of n, I would subtract its mean, and divided by its standard deviation, which is the square root of n sigma, right? Remember, to standardize any random variable, you subtract its mean, you divide it by its standard deviation. If I wanted to standardize the sample mean, I take x bar minus its mean divided by sigma over the square root of n. Now remember, I'm dividing by the standard deviation. The standard deviation is the square root of the variance. So I have these two results. Now, why do I care about this? Because I roughly want to tell you what the central limit theorem says, okay? So the central limit theorem, which just about everybody in the whole world calls the CLT, it says the following: under appropriate conditions, as n gets large, and it doesn't have to be infinity. Large could mean 8 or 10 or 20, depending on the skewness of the random variable. As n gets large, S of n star and x of n star both approach the normal, standardized normal distribution. That's an unbelievably important fact. It's the highlight of the entire course. This says if you have a sequence of independent, identically distributed random variables, and by the way, they don't have to be identically distributed either. I'll talk about that later on. But if you have identically distributed independent random variables, a sequence of them, then their sum and their sample mean both approach the normal distribution. That means we have an incredibly easy way of solving so many problems, assuming n is sufficiently large. For example, we already know, suppose you look at a binomial distribution with parameters n and p. Remember, we showed that the random variable x can be written as a sum of n indicator random variables. Each of these had, each of x of I was p, and each of these was P times Q. So that means this random variable, which is the sum of these, this is really S of n in this case. I can compute probabilities involving this if n is large enough using the central limit theorem to be illustrated. Similarly, I could do the same thing with a Poisson random variable. I could do the same thing with a geometric random variable or the negative binomial random variable. I could do the same thing with many continuous random variables, uniform continuous random variable, the exponential random variable, any random variable. So that's one remark. So again, I'm just giving you an overview of what's coming next in our next class. The second remark is, so the CLT will enable us to accurately solve difficult problems. Now, I want to make a remark. The remark I'm making is limited to discrete distributions. Let's suppose I have a binomial distribution as an example, and I want to compute the probability that x lies between 20 and 70. Notice for a binomial, x can only take integer values. Now, that wouldn't change if I did this, would it? These two in the real world would give me the exact same answer. Because if x is between 19.5 and 70.5, since x can only take on integer values, I'm really saying x is between 20 and 70. But guess what? If you make this correction for discrete random variables, you get better accuracy. This is called the continuity correction. By making this change, which doesn't affect the exact answer, it always improves the answer. Of course, as n gets larger and larger, both answers will give you the same, using the central limit theorem, but this is pretty neat. Suppose x is, for example, Poisson. And I want to compute the probability that x is greater than or equal to 15. Well, remember the Poisson also only takes on integer values. What I could do is I could do this problem instead. In the real world, the answers are the same since x can only take on integer values and x has to be larger than 14.5. It's really starting at 15. But again, I've used the continuity correction. So I want to emphasize the continuity correction is used only for discrete random variables. We do not use this correction for continuous random variables. Why? Because there's no need, because what we're doing is we're really replacing a discrete random variable which has jumps or steps by a smooth curve. So the continuity correction takes care of these little jumps and stuff. We don't need to do that for continuous random variable because we don't have those things. If you look at the CDF of a random variable, continuous random variable, remember, for a continuous random variable, if you look at the CDF, it always looks something like this. For a discrete random variable, it always looks something like this. Ultimately gets to 1. This one has jumps. So this is discrete. This is continuous. We don't have to worry about these jumps in the continuous case. Okay, so let me stop sharing screen. The exam will cover through the normal distribution. I sent you a calendar with links of what's happening over the rest of the semester. I sent you that last Monday. I will continue with the central limit theorem in our next class. I set up a special review on Tuesday, which I'm going to record for you as well. So if you need the review, please attend. It's optional, but I think it wouldn't hurt you to attend. I'll take any requests on problems that you have at that time. Look at some of the problems I worked out for you. If I get a chance, I'll do 1 or 2 on the normal distribution as well. If anybody has a particular request, send it to me and I'll make sure to include that problem in the samples that I do. Please do the student faculty course evaluations. That's really important for all your teachers, all your instructors. So please do those. Let me stop the recording